Great to have you join me tonight, maybe this morning. Um, just have to quickly share the link, the group, so we can all be on the same page. Send the link to the group quickly. Share. So the link has been shared. So today we're taking the course. It's a continuation of the class MTH 105. So sorry about that. Let's quickly do this. Yeah, I think that's better. So yesterday we did the course. Um, we treated matrix 6 yesterday, and we we were able to establish the determinants, the inverse, and a lot more. So tonight we will be taking the theoretical part of matrix of MTH 105. Okay, so we've gone a bit far. So we've taken logic, reasoning, and the link has been shared to the class. So while we wait for them to join us, then we just go ahead and get to. Please, if you are just joining us for the first time, do well to let us know your department and where you're coming from. Okay, Mr. Daniel is with us. Awesome. Great to have you, Mr. Daniel. So it's pretty late at night. It's midnight already. I'm just getting back from work, very exhausted. Um, I wouldn't want to keep us for long tonight, so we'll just go through one or two things very quickly. Then we can call it a day. We can wrap it. So very quickly, we'll be going through. Okay, Mr. Julas is here. Great to have you, Mr. Julas. Thanks for joining tonight. So let's just go straight into it. So by now, I believe we know some certain terms already, the definitions, and we know what logic is. By now, we know what logic is. I just want us to go through very quickly the theoretical part of this course, because this course is going to be covering both the theoretical part and the calculation aspects. So very quickly, we'll just go through the theoretical part tonight, and we will, so that we can get a knowledge of what some definitions and some terms are. So the first thing on our list today, excuse me, my phone just slide there. So we have the first thing on our list we'll be talking about. I'm just trying to scroll down very quickly. trying to scroll down. Okay, get the page very quickly. Just 1 minute. Okay, where are we, please? Mr. Jolas, we're actually starting from mode one, but we're just going to pick some very quick definitions of terms, of some terms, and we can move on very quickly. Yeah, we're starting from mode one, but this time around, we are just going to pick some definitions, the terms, some terms, and what they mean and their definitions, just very quickly. So, from content one, which is from the main content from module one, unit one, we have the definition of mathematics, which we are meant to understand that mathematics is the science of numbers and shape. Okay, Mr. Jolas is still MTH 105, still the course MTH 105, but we are taking the theoretical aspect of it today. 78 105, taking the theoretical aspect of it today. So, talking about mathematics, mathematics is said to be science of numbers and shape, and it can also be applied to some real life happening. So we have examples which include arithmetic algebra, and arithmetic algebra means the using of symbols or letters. Symbol in context is a letter that is made to represent a statement or an argument. So we have that as that. Then we'll scroll down to what we call logic. We said logic in our previous class. We've been able to establish what logic is, but we're just going through the theoretical part now. So we just want to talk about logic a bit. So logic is a science of reasoning or explaining events. Just very short and simple. It's a science of reasoning or explaining events, and we have that as that. So we have some objectives of symbolic logic reasoning. Now, what are the objectives of symbolic logic reasoning? We have it could be used to ascertain, analyze complicated business arguments. Now, it could be used also to decode equivalent, negation, or contradictory proposition. Now, it also be used to analyze a statement. We have it could be used to form composite statements from simple ones. So those are the objectives of logic. So now another definition of logic is said to be logic is a declarative statement or an expression of words which are either true or false, but we cannot assume both. So we have that as that. So we have the types of statements. We have basically two types of statements. We have the simple statement, we have composite statements. So the simple statement, that we have the composite statement. Composite statement can also mean compound statement. So we have that as that. I think one of the TME questions, we have the question that looks like our example here. Gary is made out of dash and two. Gary is made out of cassava and 2 plus 2 is equals to 7. I think we have that as one of our questions. So we have that as that. So we're talking about connectives now. Connectives, they are expressions, they are faces or symbols that are made used of to join, to combine two or more simple statements. Keyword there is that connectives are basically words joiner. They join two or more simple statements together. And we have types of the examples of connectives. We have the conjunction, which is the and. We have the disjunction, which is the or. We have the negation, which is not. We have conditional, which implies that. If implies that. Then we have the by implication, if and if only. If and if only tomorrow is Sunday, then I'll go to church. So by implication statements. So we have the tautology and contradiction. It is said that the negation of a contradiction is a tautology. So while the negation of a tautology is a contradiction. So you have that as that. So you have an argument. We said an argument is formed when the conjunction of a set of simple mathematical statements gives rise to another mathematical statement. Then we can have an argument. An argument is said to be when a mathematical statement, when the coming together of the mathematical statements give another rise to a mathematical statement. Then we can say we have an argument. So an argument may be valid or invalid. You know, that might be valid or invalid. So we have that as that. Okay. Okay. Let's just go down. Let's just go down. Okay. Let's just scroll. Now we are on trying to scroll down, moving past all the statement and all the has to do with algebra, proposition. All these are calculations. And our goal for tonight is just to get definition of some terms. And okay. So we have what we call definition. So we have matrix algebra. Now we are now in unit 2. We are going to be talking about matrix algebra. Matrix algebra is a mathematical model which allows enumeration, display, manipulation, and processing of both small and large volume of vectors. Vectors in the sense that numbers in the context easily in order to achieve a desired result, meaning that the algebra of matrices is said to be a process that allows the enumeration, the manipulation, the display, and processing of numbers to achieve desired results. So we have a matrix is a rectangular array. What we discussed just now was just was algebra of matrices, but now we're talking about what a matrix itself is. A matrix is a rectangular array of numbers with reference to specific rules governing the array. Matrix is a rectangular array as the first keyword, then it's with reference to specific rules governing the array. Okay, Mr. Julas, he just asked, he wants to know the page. We are on soft copy here, showing page 32, units 2, page 32. I don't know what the page number is on the hard copy, but here I have page 32 of unit 2. Are we together? Mr. Julas, are we together? Let me assume we are together on this. So just continue. We've talked about the algebra of matrices. Now we're talking about, trying to get my screen correctly. So now it's the definition of a matrix, and we said it is the rectangular array of numbers with reference to specific rules governing the array. So we have that as that. Then we have square matrix. Now it is said here that any matrix which has the same number of rows and column is called a square matrix. Any number that has same number of rows and column is called a square matrix. So under that we have the types of matrix. We have the so under the types of matrix we have the 0/null/void matrix. 0, they are interchangeably used. We have the 0, we have the null, we have the void matrix, and these are said to be any matrix of dimension with all its elements equals to 0. Then we said elements are the numbers, the arrays of numbers that makes up a matrix. So in the case of 0 or null matrix, that means all the number in it equals to 0. So we have identify matrix. Now it is a diagonal element. Now when we say diagonal, we mean something like this. Something like, let me get something to illustrate diagonal, what diagonal means. Now this is what diagonal means. A book is slant like this, then we can say diagonal. No, now identity matrix, identity, yeah, that's identity. I think we wrote identify, but identity matrix is said to be a matrix in which all its diagonal elements are 1. So this is what diagonal looks like. All diagonal elements are 1. That's an identity matrix. So we have diagonal matrix is said to be, this is a matrix that has element only on its diagonal. So now, unlike the identity matrix, which the number on its diagonal is 1, we have the diagonal matrix which has only numbers, elements. Now I said this is a matrix that has elements only on its diagonal, meaning that every other element is 0, but we only has elements only on its diagonal. So we have that. So we have the transpose of matrix. So now all these are under types of matrices. So we have the transpose. Now the transpose of a matrix is the interchanging of its row with its column, meaning you switch the row with its column. I believe we all know that because that has been treated in the class. We've treated that properly in the class. So we have that as that. So we have symmetric matrix. Symmetric matrix is said to be the matrix. Symmetric matrix is said to be the matrix which its transpose is equals to itself. That is symmetric matrix. We also have idempotent matrix. Idempotent matrix is said to be, okay, I'm coming, let me just quickly adjust my screen. Okay, now idempotent matrix is said to be the matrix if the element of its matrix is the same thing raised to the power of 2. Let's not forget we are only just doing the theoretical part. Don't be bothered much because this is just the theoretical part. So we have that as that. So we have equality of matrix. Two matrices are said to be equal if their corresponding elements are the same. That is what equality of matrix means. They are said to be equal if the corresponding elements, if their corresponding elements are the same. So we have that as that. So we have the algebra of matrices. 2 or more matrices can be added or subtracted if, I'm trying to adjust my screen here, if they, oh, come on. Okay, I'm trying to adjust my screen here. Okay, we have the algebra. Oh, why is my screen doing? That's my. Okay, let me just quickly do this here. So we have algebra of matrix, and now 2 or more matrices can be added or subtracted if they are the same dimension. When we talk about algebra, it has to do with addition, subtraction. Algebra, basically algebra is more of addition, and so it said 2 addition or subtraction. That's what algebra is all about. So two or more matrices can be added or subtracted if they are of the same dimension. So we have that as that. So one of the simple thing in matrices. So we have scalar multiplication matrices. This is multiplication of matrices. Definitely, you multiply the element of different matrices by different matrices to get your answer. According to what the name implies, multiplication of matrix. Now, for multiplication of two matrices to be possible, they must be conformable matrices, i.e., matrices A and B are conformable to the column A, has the same dimension and the row, meaning that the matrix A, the row, must be of the same dimension of matrices B, colon. The row and colon of these two different matrices must be the same. Then you can see they are conformable and you can multiply them. So we have that as that. So what else do we have here? Now we have determinant of the matrix. Before you can talk about determinant of the matrix must be a square matrix. That is the yardstick of finding a determinant matrix. The matrix has to be a square matrix. Excuse me. So we have that as that. Okay, we have singularity in matrix. A matrix is said to be singular if the determinant is equals to 0. That's singularity matrix. I think it's something we've treated previously in the previous class. Then we are moving straight on to matrix inversion. Matrix inversion. Matrix cofactor matrix. It is defined to be matrix obtained by replacing every number of the elements given to that particular matrix by the cofactor of its determinants. I think this is one of the things we'll be taking tomorrow in the class. Before we move further, we'll solve how to find cofactor of a matrix. I think it's one thing we should do before we move forward. So we have adjoint. So adjoint and cofactor, they work hand in hand. All this we'll find out more tomorrow in our class tomorrow. Adjoint and the cofactor. I think that is time for that. So we have what else on our list? Trying to scroll down so I can also some more of calculation. So I think we'll be treating basically tomorrow. So we have vectors. Now we have vectors. So we have introduction. A vector is a single row or column matrix. That is just it in short. A vector is a single row or column matrix. Short and precise. So we have that as that. Then we have under vectors, we have scalars. Scalars are quantities which are completely specified by numbers which measure their magnitude in terms of some chosen units but have no definite direction in space. Examples are speed, mass, density, time, length, work, and temperature. That is scalar. Scalar are quantities that which are completely specified by numbers. Scalars are quantities completely specified in numbers, in measurable numbers, in their magnitude, in terms of choosing word, but has no definite direction in space. So we have vector. A vector is a physical quantity which has magnitude. Excuse me, guys. I think I need to quickly get attend to something. Just a moment, please. Okay. Sorry for the break in transmission. We have a vector is a physical quantity which has magnitude and direction. It can also be defined as a directed line segment. 2 points now. Vector is a physical quantity which has magnitude and direction. It can also be defined as a directed line segment. Examples are velocity, acceleration, displacement, force. So that is examples of vectors. So we have types of vectors. We have the free vectors, we have time and related vectors, we have pointed located vectors, and we have position vector. Now the free vectors have magnitude and direction but have no particular position associated with them, e.g. displacement. Displacement is an example of free vector. Now we have time related vector. These are located along a straight line, e.g. force. Force acting on a rigid body always move along their lines of action without changing its effect on the body, meaning that force needs a body to be effective and it moves along this line of action without changing on the body. So we have point located vectors, which is a vector whose position in space is fixed in addition to its magnitude and direction. Point located vector is fixed. Is fixed in addition to the magnitude and direction. So we have that as that. Excuse me. So we have vector representation. Now a vector is represented by directed line segments where the length and direction of the segment correspond to the magnitude and direction of the vector. As you can see in the paragraph below, it explains that A and B, we have the vector A and B, and we have 0 to A. So we have, as can be seen above, a vector can be represented by AB vector and AB or A vector. So we have that start. Okay. Excuse me. So exhausted. So exhausted. Okay, these are calculations which we are going to take in our subsequent class. Okay. Okay, it's the subtraction of vector. It's a more of calculation. Okay, we have the multiplication of vector. some more of calculation. And, I think at this point we would stop here so that I don't want us to go far into this, so when we are doing the calculation we won't be too behind, we won't be lagging behind. Like the matrices are we've spoken about, we've done a lot of calculation, we've treated a lot of solution problems on it, so we can relate to some extent. But for vectors, let's just call it a day here, because as soon as we are done with tomorrow's class, our next class we'll be moving into something different. So thank you very much, guys. I hope tonight's class has been helpful, and I hope you've gotten a thing or two from tonight's class. Let's do up to the assignment. An assignment was given in the previous class. That was yesterday. If you are yet to submit the assignment, please do up to submit the assignment, and you can move. You can all be on the same page. Thank you very much, guys. Thank you for sticking around. I look forward to seeing you in the next class. Bye.